In today's session, we get to talk about Archimedes' principle. Now, for us to understand Archimedes' principle, we need to first get well versed with what we mean by upthrust. So allow me to first explain what upthrust is and where it comes from. Now, first of all, when an object is put in water, like the one you're seeing, it experiences forces in all directions in this liquid. It will experience forces in that direction. It will experience forces in that direction. It will experience forces acting down on top of it and experience forces down on it. Of course, we all know that it's a property of pressure in liquids that pressure acts in all directions. So if you look at this solid, forces are acting on this solid from all directions. However, when you look at the forces on the sides, the forces on the sideways will always cancel out because they are more the same. So they will cancel out. But the forces acting downwards from down here are greater than the forces that are acting upwards. And as a result, the resultant in this case is such that we always have an upward force acting upwards. That upward force that acts upwards on this solid as it's in water is what we are calling the upthrust force. It's like when you drop in water and you are a swimmer, you always feel a certain kind of resistance acting on you in the upward direction as you're trying to move in water. That is for people who know how to swim, or if you've ever played around in a lake. When you immerse yourself fully in water, you always feel a certain resistance as you advance towards down. That resistance is the upward force acting on you, and that's what we are calling the upthrust force. Now that we have understood what upthrust actually means, now let's go on and describe the Archimedes principle. Now, the Archimedes principle simply put that when a body such as this one is partially or fully or wholly immersed in a fluid such as this, it is going to experience an upthrust force, and this upthrust force it is experiencing is supposed to be equivalent, or it is equal to the weight of the fluid that has been displaced by that solid. It's as simple as that. So this upthrust force, which is also known as the buoyancy, is simply the tendency of the liquid to exert an upward force on a body that is immersed inside it. As simple as that. So let's go ahead and do an example where we are required to use this Archimedes principle. A string supports a solid iron object of mass 0.18 kilograms totally immersed in a liquid of density 800 kilograms per meter cubed. Calculate the tension in the string if the density of the iron is 8,000 kilograms per meter cubed. First of all, we need to summarize the question. We'll do it diagrammatically. The question says that a string supports a solid iron object of mass 0.18 kilograms. So we are having a string right there. It is supporting this thing right there. And this thing, the weight of this thing is 0.18 kilograms. So meaning that this solid object, this iron object, the weight of this iron when it is in air is 0.18 kilograms. That is the weight of this thing. Now, the question says that a string supports a solid iron object of mass that totally immersed in a liquid. So this thing is totally immersed in a certain liquid. This is the iron. It's totally immersed in a liquid whose density, so the density of that liquid is 800 kilograms per meter cubed. They're asking us to calculate the tension in the string. Calculate the tension in the string if the density of iron is that. So the density of the iron, let's call it the density of that solid, is 8,000 kilograms per meter cubed. Yeah. So the density of that solid iron is 8,000. And they want us to find the tension in the string. Now, for us to find the tension in the string, I think there are two ways for us to do this. To begin with, the weight of this solid, let's say if this was, we had a spring balance here. This thing, at first probably it weighed 0.18 kilograms when it was dangling in air. If it is dangling in air and that is its weight in air, oh, by the way, this is not weight, this is mass. This is the mass in air. So it means that if we want to find the weight of this thing in air, its weight in air is going to be equal to its mass, 0.18 kilograms. Multiply that by the acceleration due to gravity, which is going to be 9.81. So it means that the weight of that solid when it is in air, it is going to be equal to 1.7658 newtons. So that is its weight in air. So now again, if it was dangling in air, it would mean that it would weigh 1.7658 newtons. Now this 1.7658 newtons would be the tension this string will be experiencing. Because let's face it, if this thing was in air like that alone, this is the weight of this thing as it's acting downwards. It means that the string is experiencing an equal but opposite force. So if this thing weighs 1.7658 newtons when it is in air, it means that if this body was dangling in air, it would be the tension experienced in the string would be exactly 1.7658 newtons. Now, the scenario we are having here is that this thing right there is immersed in a liquid. If it is immersed in a liquid, the string is still experiencing a certain tension. So if it is immersed in a liquid, it means that the weight this thing is experiencing while it's in water is the same as the tension experienced by this. So meaning that the weight of this in water is equivalent to the tension experienced by the tension experienced by the string. So it means that it is as simple as that. That for us to be able to find the tension in the string, we simply have to find the weight of this iron in water. But well, I think we shall use that approach as an alternative. Right now, this video is about how we can use Archimedes principle to find this, to calculate this. So I'm going to first use Archimedes principle to find out the tension in this string. Then we can use this other alternative that I have just been explaining. So let's get started. First of all, this string, as it is here, this object, when it is in water, there are some forces that it is experiencing. If I may redraw that here, this is the iron solid. It is on this. This thing is immersed in water. And when it is immersed in water, it is experiencing tension. This tension is acting in the opposite direction. But while this thing is in water, this solid, it is experiencing some forces downwards. We have the weight of this thing acting downwards. The weight of the solid. Then upward, we have the tension acting in that direction. And also, because this thing is immersed in water, there is the upthrust force acting on this body. So for this to balance up the forces, we would say that first of all, the tension that is the upward forces are equal to the downward forces. So meaning that the tension experienced by the string upwards plus the upthrust is supposed to be equal to the total weight of this body acting downwards. Weight of the solid acting downwards. So now, what are we interested in? We are interested in the tension. So when we make tension the subject of the formula, it means that tension here, the tension experienced in the string is given by the weight of the solid when it is in air minus the upthrust. So our task is to find this and that, and then we will have the tension. So now, what is the weight of the solid in air? Of course, the weight of the solid in air is already given. We already found it here. The weight of the solid in air is 1.765 newtons. So it means that one we have it. We have the weight of the solid in air. So now our role here is to find the upthrust here. So now for us to go ahead and find the upthrust, we will derive the way we get upthrust from Archimedes principle. When we were beginning this session, we said that Archimedes' principle simply states that when a body is partially or wholly immersed in a fluid, it's going to experience an upthrust, and this upthrust is equivalent to the weight of the fluid that is displaced. So for us to be able to get this upthrust force right there, it is as good as getting the weight of the fluid displaced. So the question is that what is the weight of the fluid displaced? If we know the weight of the fluid that has been displaced, then we have the upthrust. So let's concentrate on first getting the upthrust first. So upthrust is going to be equal to weight of fluid displaced. Now we know that weight is given by mass times gravity. Now we already know the gravity, we need the mass. Now we do not know the mass of this fluid. It's not given in the question. But we know that mass is also given by density times volume. So for us to get the mass of the fluid, we need to get the density of the fluid, or let's call it the density of the liquid. Multiply that by the volume of the liquid. Volume of the liquid, multiply that by the gravity. So what does that give us? Now the density of the liquid is given, it is 800 kilograms, the density of this liquid. So the density in this case here is 800, multiply that by the volume of the liquid displaced. If you realize the volume of the liquid displaced is the same as the volume of the solid that is displacing. So it means for us to get the volume of the liquid that was displaced, it is as good as getting the volume of that very solid, because this very solid, it can only displace its own volume of water. So it means that it's going to be the volume of the liquid displaced is the same as the volume of this solid. So the volume of the solid, since we do not have it directly, we can get it from the mass of the solid divided by that by the density of the solid, and multiply that by gravity, which is 9.81. So this is going to become 800, multiply that by, this is the volume of the liquid, this is volume of the liquid that is displaced is the same as the volume of the solid itself, which is given by the mass of the solid. The mass of the solid in this case is given in the question as 0.18 kilograms. The mass of the solid in air is 0.18 kilograms. 0.18 kilograms, divide that by the density of the solid, which is also given in the question as 8,000 kilograms per meters cubed. Multiply that by the gravity, which is 9.81, and that gives us an answer of 0.17658 newtons. So that's the upthrust force. Now that we have the upthrust force, we shall now go back and find the tension in the string. So it means that the tension is given by the weight of the solid minus upthrust. In this case, the weight is already given in the question. We already got it as 1.7658. Of course, this figure is gotten from here. This is the weight we got earlier, 1.7658. Subtract from the upthrust, which we've just gotten here as 0.17658. And when we subtract those two, we shall end up with 1.58922 newtons. And that is the tension experienced in the string. Now the alternative way of doing this is this. First of all, this string supports a solid iron object whose mass is 0.18 kilograms. So the mass of this solid iron, let me call it M subscript I, is 0.18 kilograms, and definitely this makes its weight, the weight of the solid iron is now 0.18 kilograms. Multiply that by the acceleration due to gravity, which is 9.81, and that gives us the weight of the solid iron as 1.765 newtons. And this is the weight of the solid iron when it is in air. So now, of course, it is totally immersed in a liquid of that density. So the density of the liquid we are talking about here is 800 kilograms per meter, and we are required to calculate the tension in the string. If the density of the ion in this case is 8,000 kilograms per meter cubed. Representing this diagrammatically shows this is the solid ion. Now representing this diagrammatically means that this solid ion is immersed in a certain fluid. And if it is immersed in a certain fluid, it means that this string with which it is immersed within the fluid is experiencing a certain tension. So in other words, if they want us to find the tension that is experienced in the string, it's another way of asking us to find the weight of this solid ion when it is immersed in the fluid, because the weight of this solid ion when it's immersed in the fluid is equivalent to the tension that is being experienced in this string. So it is as simple as getting the weight of that solid ion. So to get started with with the calculations for the weight of the solid ion when it is immersed in this liquid, we shall begin by saying that relative density of a liquid is going to be equal to the apparent loss in weight of this solid ion when it is placed in this liquid, so which is going to be the weight of this solid ion when it is in air minus the weight when it is in the liquid. Divide that by the weight when this solid ion is in air minus its weight when it is in water. So what we want here is this. We want to find the weight of this solid ion when it is in the liquid, and this weight is equivalent to the tension that is experienced by this string when it is in the liquid. So we need to find the rest of these parameters. So to find the rest of these parameters, we shall begin off first with the weight of this solid ion in air. The weight of the solid ion in air, we got it here as 1.7658 newtons. So it means that we already have that weight in air. So let's go ahead and find the relative density of the liquid. Now from our question, to find the relative density of the liquid, we know that the primary definition of relative density, we know that relative density is given by the density of a substance, divide that by the density of water. And in this case, the density of the substance here, we are looking at this fluid or the liquid. The density of the liquid is 800, so it means it's going to be 800 kilograms per meter cubed. Divide that by the density of water, which is 1000. And this is going to give us 0.8. That is the relative density. So meaning we found the relative density of the liquid. The relative density of the liquid is 0.8. So that is done. Now we need to find this, the weight of the air minus the weight of the water, or call it the apparent loss in weight of the solid when it is immersed in the water. Now of course we have the weight of the solid in air that has been given. We already have it. We already calculated it. But we do not have the weight of the solid in water. It's not given anywhere in the question. But if you think harder about this expression, the apparent loss in weight of the solid can also be found in another equation. The relative density in liquids is given by the apparent loss in weight of a substance in the liquid, divide that by the apparent loss in weight of a substance when it is immersed in water. Likewise, when you're trying to find the relative density in solids, it's given by the weight of a substance when it is in air. Divide that by the apparent weight in loss, the apparent loss in weight of that substance when it is immersed in water. Now you realize that this expression in the denominator is the same as that expression in the denominator. Now getting back to our question, you see that in our question, one of the parameters that we need is that we need to find this expression, the apparent loss in weight of the substance when it is immersed in water. And if you look at our expression for relative density in a solid, you realize that it is the same expression in the denominator. In this question, we are dealing with the relative density of an ion that is immersed in water. So it means that if we attempt to find the relative density of that ion while using this expression, we will be able to find the expression here, which is exactly what we are looking for here. So we shall go ahead and attempt to find the relative density of the solid. So to find the relative density of the solid, we shall say relative density of the solid ion, let me call it that, is going to be equal to the weight of the solid ion in air, divide that by the apparent loss, which so happens to be the weight of the solid in air minus the weight of that same solid, ion solid in water. If I may write this here, this is the same as saying relative density. Now you realize that the relative density of the solid ion when it is in air is given by the density of the ion. So it's going to be density of the ion, divide that by the density of water, is still going to give us the weight of that ion in air, divide that by WA minus W subscript W. So the density of this ion when it is in, the density of this ion according to the question is 8,000, divide that by 1,000. This is the density of water, so this is the relative density of the ion, is given by its weight in air. Now we already know its weight in air, it was given to, we found it out earlier. Its weight in air is 1.7658 newtons. So this is going to become 1.7658 newtons, divide that by WA minus WW. So we shall end up with, when we make this the subject of the formula, WA minus WW, which we are most interested in, the expression, is giving us 0.220725 newtons. So looking back at where we've come from, we already have the relative density of the liquid. We got it as 0.8. We have got this expression, which is this right here. We have the weight of the solid ion in air, so we can go ahead and make WL the subject of the formula, and we're able to get the tension in the string. So to proceed with that, we shall do, if I may write this down, so the relative density of the liquid, we got that already as 0.8, so this is going to become 0.8 is equal to the weight in air, which we already got, the weight of the solid ion in air, which we got as 1.7658 newtons, minus the weight of the solid in the liquid, which we are looking for, which is equivalent to the tension, divide that by this expression, which we already got as 0.220725 newtons. So when we make WL the subject of the formula, we shall end up with 1.58922 newtons. And so this happens to be the tension that is being experienced by that spring. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia, helping you manifest excellence.